Good afternoon, class. Here's chapter 5, integrals, section 5.4, the substitution rule. This is the last section for chapter 5 for integration, so the substitution rule. We covered 5.1 through 5.3, the FTC, and now the substitution rule. Reminding you of various integration formulas, a constant depending on the variable that it indicates here. The answer is in this case kx plus c. The power rule, x to the power n is 1 over n plus 1, x to the power n plus 1. The constant multiple, sum and difference. X to the power of -1, e to the power of kx, sine, cosine, trigonometric functions, and so on. We added the FTC. The derivative of the integral of a to x f of t dt is f of x. Again, evaluated this at the upper variable, and the integral of a to b lowercase f of x dx is capital F of b minus f of a. Granted, capital F prime must be lowercase f of x. And here's the substitution. The integral of f of g of x g prime of x dx is the integral of f of u du, where u is g of x, du is g prime of x dx. So let's go over that and see what's going on. Section 5.4, the substitution. Integration by substitution is the reverse process of the chain rule in differentiation. So if I want to differentiate this, I'm using the chain rule. So capital F prime g of x times g prime of x. So if I want to differentiate that, capital F prime g of x, g prime of x. And normally, we use capital F prime as lowercase f, or the derivative of capital F is lowercase f. The integral of lowercase f is the capital F, of course, one of those antiderivatives. So f of g of x, g prime of x. So I hope you see, if I differentiate from the left side and I get to the right side, if I integrate from the right side, I must get to capital F of g of x, which is the reverse process of the chain rule. So having said that, we go with the substitution. We let u represent the inner function g of x. And then du dx is g prime, and du is the product of these two, g prime of x dx. And so the integral of f of u du gives you capital F of u plus c, which is capital F of g of x plus c. Over any interval for which u equals g of x is continuously differentiable and f is continuous on the range of this function, the following relationship holds. The integral of f of g of x, g prime of x dx, where we call g of x u and g prime of x times dx du, we get the integral of f of u du, capital F of u plus c is the answer, and you replace the u, capital F of g of x plus c. It is important to start with u and du. You have to let the reader know what is the choice of u and du. For example, here, we have the integral of 2x x squared plus 5 quantity cube dx. Here's the tip. Look for a function u equals g of x anywhere in the integral, and its derivative du or g prime of x multiplied by dx. That is the methodology. Now, what are we dealing with here? We have a product. This is a product of a polynomial and a polynomial. Where two polynomials are involved, normally the more complicated one is a choice of u. Clearly, this is more complicated, so that would be the choice of u. So u is x squared plus 5. If I differentiate this, that means du dx, I get 2x, and du is the product of these two. Normally, we skip this step and we write du is 2x dx. Now, I can't emphasize this enough. When you show work, you must first and foremost let your reader know what is u and therefore what is du. Otherwise, it's wrong. It can't be in your head. It has to be on your paper. I can't emphasize this enough. So having said that, to make sure this makes sense to everybody, we're going to move things around, and I'm going to put 2x next to dx, and therefore clearly This is u, this is du. By the way, before we move on, one might say, okay, I can raise this to power of 3, and that works fine. But what if instead of 3, you have 300? That's why we go with the substitution. So having said that, we are looking at the integral of u cubed du, which uses the power rule, 1/4 u to the power of 4 and a constant. Finally, back substitution, 1/4 x squared plus 5 to the power of 4 plus a constant. This is the final answer. That's the method of substitution. So here's another example, everybody. The integral of 3x squared, parentheses x cubed plus 1 to the power of 10 dx. And remember, you have polynomials are being multiplied by each other. So the more complicated one is the choice of u. And you also notice that the derivative of this parentheses is 3x squared. In other words, note that 3x squared is the derivative of x cubed plus 1. So let's rewrite it by putting 3x squared next to dx. So clearly, this is the choice of u. This becomes du. Substitution. Let u be x cubed plus 1. Du becomes 3x squared dx. So you have to write this first and foremost before you move on. You must write this. So we have the integral of u to the power of 10 du. Now we use the power rule, 1/11, u to the power of 11 and a constant. Reverse substitution means replace the u with x cubed plus 1. This is the final answer. By the way, whether you write it in this fashion or you write 1/11, and then x cubed plus 1 to the power of 11 means the same thing. This is the final answer. The integral of 9 times x squared plus 3x plus 5 times 2x plus 3 times dx. Clearly, we are dealing with a couple of polynomials that are being multiplied. You can distribute, but we want to continue with substitution. So obviously, this is more complicated. That makes sense to be the choice of u. So u is x squared plus 3x plus 5. Its derivative is 2x plus 3, which makes du 2x plus 3 times dx. So again, you have to write this first and foremost. Now, obviously, this is u, this is du, and we have the integral of 9u du. In other words, you can't just go from here to here without writing this. You can't do that. Again, a simple case of a power rule, 9/2 u squared plus a constant. Reverse process means replace the u. We get 9/2 x squared plus 3x plus 5 quantity squared plus a constant, and we are done. The integral of 5x to the power of 4 e to the power of x to the power of 5 dx. Here's again a methodology that you want to remember. If we have an exponential involved in integration, normally the exponent is the choice of u. So if u is x to the power of 5, its derivative is 5x to the power of 4. That means du dx. So what is du? 5x to the power of 4 dx. And so we are going to move things around. In other words, move this one next to dx to make sure it is clear to everybody that we are dealing with e to the power of u du. Again, this has to be written. This can't be Just in your head, it has to be on the paper. Now, the integral is itself e to the power of u and a constant, and reverse substitution. Replace the u. The final answer is e to the power of x to the power of 5 plus a constant. The integral of x to the power of 4, e to the power of x to the power of 5 minus 2 dx. How do we deal with that? As mentioned here, when you have an exponential, the exponent is a choice of u. Now, whether u is x to the power of 5 or x to the power of 5 minus any number, du is the same thing because the derivative is 5x to the power of 4, so we have the same du. Just as we did here, we're going to move x to the power of 4 next to dx, and we notice over here we had the du, over here we don't have a du. So what's the difference? Number 5 is missing. So what most texts, including yours, do, they do solve for dx. But there's a better and easier and faster way. Because 5 is a number. I can put the 5 here. How do I undo it with its reciprocal 1/5? You make sure the product of these two numbers is 1. Then you're fine. Again, this can only be done if this is a number. If anything else is missing, is a different story. It's a different methodology. Again, can you solve for dx and do the work? Yes. But this is much faster. And if you solve for dx, it will create that 1/5 in front. So now we're going to replace this. We get 1/5 the integral of e to the power of u du. Again, the same answer as here, and we keep the 1/5 in front. And reverse substitution gives you 1/5 e to the power of x to the power of 5 minus 2 plus a constant. Again, I'm going to stick with this method, but I just want to mention, just in case, everybody, over here, what many do, they solve for dx, which makes it du over 5x to the power of 4. And so instead of putting this 5 here and 1/5, they are going to put this one instead of the x, which creates the 1/5 in front. So this is the method in case some people are familiar with, but believe it or not, what I just mentioned is a lot faster and easier. All right, what happens in both cases, you're dealing with a fractional form. This one more specifically is a rational function. Why is it a rational function? Because the top and the bottom are polynomials. This one is not, because e to the power of t or 5 plus e to the power of t, they're called transcendental functions. And so having said that, what is the methodology when you're dealing with a fractional format? The very first step, can I simplify? If I can, I must. If not, I'm going to move on. This can't be simplified. The denominator is a choice of you. If I differentiate du dt, I get e to the power of t, which makes du just e to the power of t dt. It is extremely important to know dt always belongs to the numerator. So I'm going to rewrite it. So it becomes clear that we have du over u. And as you know, it follows that the answer is a natural log. So it's natural log of absolute value of u plus c. We replace the u, and because 5 plus e to the power of t is positive, in fact, it's greater than or equal to 5, we can drop the absolute value. If you have doubts, you can. What about here? When you have a rational expression, again, the very first step is to simplify, meaning If you can find a common factor between the top and the bottom, you drop it. Now, first, if the numerator has a degree larger or equal to the degree of the denominator, you have to divide either by long division or synthetic division. You can't emphasize this. But if it's the other way around, you just see if there is any way to take a common factor. And to do that, you want to factor this, even if it can be factored, and it doesn't have a factor of x plus 1, doesn't do us any good, but it can't be factored. How do we know that? I want to remind you of something we learned in elementary algebra. The quadratic formula ax squared plus bx plus c equal to 0 gives us x equals minus b plus minus the square of b squared minus 4ac over 2. B squared minus 4ac is called the discriminant. Why? Because it gives us a lot of information. When b squared minus 4ac is positive, we have two distinct real solutions. When it's 0, we have one real solution, which is a rational solution. When it's less than 0, no real solution or two complex solutions. Also, if it's a perfect square number, then this can be factored. So if we calculate that, in this case, I hope you see that A is 1, B is 2, C is negative 1, B squared, 2 squared, minus 4A, which is 1, C, which is negative 1, results in 4. And 4, 8. Remember, minus 4 times 1 times negative 1, this is positive 4. And 8 is not a perfect square. It can't be factored. We're done. So therefore, because we can't factor it, we're going to pursue and say u is the denominator. Now, if you differentiate, the u dx becomes 2x plus 2, which is 2 times x plus 1. So du is 2 times x plus 1 dx. We're going to rewrite this by putting the dx at top, and we notice the denominator is u, but the numerator is not du. Why not? 2 is missing. So a multiplier 2 is missing. You can solve for dx, or just the easy way out. Put the 2 and its reciprocal, 1/2. By the way, you can put both of them inside if you want. It doesn't matter. But the fact of the matter is you have to choose such that the product equals 1. That's the only way that works. So the top is du, the bottom is u, and the 1/2 remains outside. It remains as a coefficient, as a multiplier, doesn't go away. Again, this is a natural log, just as it was here. And 1/2 ln of absolute value of u plus a constant. U must be replaced. And the final answer is 1/2 ln of absolute value of x squared plus 2x minus 1 plus a constant. And we keep it in an absolute value because the expression x squared plus 2x minus 1 can be positive, can be negative, whereas here the expression 5 plus e to the power of t is always positive. Now, I want to discuss the reciprocal of those, and let me erase the word. As I mentioned, for this one, if it was a reciprocal, because the degree becomes larger, you have to divide. Long divisions, in this case, can be also synthetic division. And then you have the quotient, and then the remainder. The quotient becomes a simple case of a power rule. You work on the remainder. What about this one? You make up two fractions. This one, 5 e to the power minus t. This one is just 1. This one is itself times negative 1, so minus 5 e to the power minus t. This one is plus t and a constant. And that's the final answer, everybody.